we step on the brakes in a car, we just expect it to stop. But have you ever thought about what's actually inside that little brake pad doing all the hard work? It's a surprisingly complex world.
It absolutely is. People think it's just one material, but it's a composite, a recipe. And a huge part of that recipe is the reinforcing fiber, which basically holds everything together under extreme stress.
Let's start with a common one then, rock wool. I see it's a recycled mineral fiber used for its high tensile strength, and it can handle temperatures up to 870 degrees Celsius. It also bonds well with the other stuff in the pad, and it's relatively cheap.
That's the appeal. Rock wool's heat resistance and low cost are its big selling points. The trade-off, though, is its brittleness and the potential for creating airborne pollutants during manufacturing.
What does that brittleness actually mean for a brake pad in the real world?
Well, think about a hard stop or hitting a pothole. That brittleness means the rock wool fibers can fracture more easily. This doesn't just compromise the structural integrity of the pad over time. It can also release fine particulate matter, which impacts both the lifespan of the pad and the environment it operates in.
I see. So, rock wool is great for cost and can handle the heat, but its brittle nature limits its use in really high-stress situations. So what's the next step up, say, ceramic fibers?
Exactly. After asbestos was phased out, ceramic fibers became a key reinforcement material in non-asbestos pads. They offer a high coefficient of friction, fantastic resistance to heat and thermal shock, and just superior mechanical properties overall. They really boost the pad's durability.
That sounds like the perfect material.
It's definitely the performance A student, but the major hurdle is cost. It's an advanced material, and that drives up the price of the final brake pad. Plus, the application technology is still being fine-tuned to perfectly meet all the real-world operational demands.
Right, so you get that premium performance, but it comes with a premium price tag and some ongoing technical refinement. Is there a material that tries to find a middle ground? That brings us to composite mineral fibers, or FKF.
Yes, FKF. This has become the go-to reinforcing fiber in many non-asbestos brake pads. You'll find it in everything from disc brakes on passenger cars to heavy-duty drum brakes on trucks. It has good friction and wear characteristics, better heat resistance than asbestos, and it really hits a sweet spot between performance and cost.
It sounds like a versatile all-rounder.
It really is. FKF is a true workhorse. The one tricky thing, though, is that during the mixing process, it has a tendency to clump together due to static electricity.
Why is that clumping such a big deal? Isn't that just a manufacturing headache?
It's more than that. It directly affects the consistency of the final brake pad. If those fibers aren't perfectly and evenly dispersed, you can get spots with an unstable friction coefficient or uneven wear. For something as critical as a brake pad where you demand consistent, reliable stopping power, that kind of variability is a huge problem. It's a perfect example of where the tiny details in manufacturing determine the final performance.
That makes sense. So even with this great all-rounder material, the process is everything. When you look at all three, what's the big picture here?
The big picture is that there's no single best fiber. Rock wool is a solid, cost-effective choice, but you have to accept its brittleness. Ceramic fibers offer incredible performance, but at a high cost and with technology that's still evolving. And FKF is this fantastic, versatile option that balances everything, but it demands a very precise manufacturing process to overcome its mixing challenges.
So the choice of fiber is really a high-stakes balancing act.
Absolutely. At the end of the day, selecting the right fiber for a brake pad is a critical engineering decision, a constant trade-off balancing performance, durability, and cost.